So today we're going to turn our attention to the actual mathematical relationship between what amount of products and what amount of reactants we have, the concentrations. Specifically, we're going to look at what's happened after the system is allowed to carry out the reaction and is allowed to reach a point of equilibrium. So in this case, the initial concentrations, whatever we started with, makes absolutely no difference. All we need to look at is what are the concentrations of the substances at the end. We do that by looking at something called KEQ. Now, in chemistry, we're going to be looking at a lot of different Ks, and K just stands for constant. EQ means we're talking about an equilibrium constant. Now, the way we get the equation for that is we take a look at the chemical reaction. Chemical reaction is going to be made up of a number of substances. I've picked 4 just because. The small letters A, B, C, and D will represent coefficients, numbers 2, 3, 4, 1, etc. The big letters A, B, C, D will represent the actual compounds. So the way we get KEQ is we take the concentrations of the products, divide it by the concentrations of the reactants. That's what those square brackets means. Those square brackets means concentration. What you're going to notice about that equation is that the coefficients, or the numbers in front of the substances, actually move up and become exponents in the KEQ equation. That's just a mathematical necessity to make the math work out the way we need it to. I realize at this point developing the KEQ equation might seem a little confusing because we haven't dealt with a real example, but we will deal with that in a moment. So here we have a chemical reaction. H2 gas plus I2 gas yields 2HI gas. So to get the KEQ equation, it will be a fraction. It will be the concentration of the products divided by the concentration of the reactants. So the products, the only product we have is HI. And since we have 2 HIs, that 2 in the KEQ equation moves up and becomes an exponent. The reactants, we have 2 of them, H2 and I2, so their concentrations will go on the bottom. Notice that the 2's that are subscripted do not change. Those are part of the substance. They don't move anywhere. Notice also that when we have multiple reactants or multiple products, those concentrations get multiplied. A common mistake would be to put H2 plus I2. It's not adding, it's multiplied. So that is the proper KEQ equation here. Now we're not just going to create the KEQ equation, we're actually going to use it to determine different things about the reaction. So given that same chemical reaction, that same KEQ equation, now I've told you the concentrations of the various items at equilibrium. We can take those and we can plug those in and we can calculate the value of KEQ. We can get a number for it. And that number is going to tell us something a little bit later on. So if we take the KEQ equation, same equation we got in example 1. And we substitute in the values that we've been given. So concentration of HI was 0.156 molar. That's that's 0.156 squared. H2 and I2 were both 0.022 molar. We go and we do the math. If we want the foolproof method, we can do it in 2 steps. So we do 0.156 squared. We get 0.024336. .022 times 0.022 is 0.000484. We divide those. KEQ is roughly 50.28. As always, we need to look at sig figs. So we look at the concentrations we were given. 2 of those had 2 sig figs, 1 had 3 sig figs, so we'll need to go to 2 sig figs. So 50, but we need to show that 0 is significant. It's just unfortunate that the rounding happened that way. And we need to make that exception. So KEQ is 50. KEQ has no units. It is unitless. So it's just a straight number. Now I want to jump back to example 1 just for a moment in order to make a point about something. The states that the substances are in are important when it comes to KEQ. You notice that all of these substances were gases. And the concentration of a gas can change during a chemical reaction. In fact, the concentrations of aqueous solutions as well as gases can change. If we have a chemical reaction that has solids or liquids, we can't change the concentration of a solid or a liquid. Because a solid is not dissolved, we can't talk about how many moles per liter. Same thing with a liquid. So when we're dealing with the KEQ equation, we actually exclude all solids and liquids from that equation. And once we get to the next example, we'll see what that looks like.